Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to talk about parametric surfaces. So we've talked about parametric curves before, like a r of t equaling something like the vector like x of t, y of t, and then z of t, right, in 2D, and we can just talk about for that one, we might have some sort of curve that's just like a spiral in space or whatever. And at different t values, right? You're just at different spots or whatever. We've seen that way back in chapter 12, but we will need to talk about doing a similar thing for surfaces. So basically parameterizing instead of a one-dimensional curve, a two-dimensional surface. So I guess a two-dimensional surface graphed in 3D, much like this is a one-dimensional object graphed in, honestly, 2D or 3D or higher. So you're going to see some connections between what we've done before and where we're kind of going with this eventually. So we've done these problems where we basically do these line integrals, right, which really are like curve integrals over a vector valued curve in space like this. We're going to be able to do something similar for these parametric surfaces, and that's going to be something called a surface integral. We'll talk about that in videos here coming up pretty soon. And same thing actually up here. So lately we've been concerned with 2D regions, and we've talked about how stuff can diverge from a closed loop in 2D space. That can be understood as basically this thing called flux. You can also do flux for 3D objects. You can talk about if you have some sort of I don't know, this could represent some cell membrane or something, some sort of rectangular prism that could represent a cell. You can talk about all the stuff that sort of leaves the cell at any given spot, and that is this idea of flux still. And that's kind of more typically where we think about flux as an object and, some sort of surface. And we'd be talking about the stuff leaving that closed surface. And so these are just reasons why we will need to know how to parameterize surfaces, because the same way that we kind of work with these parametric curves to do line integrals and whatnot, we're going to need to parameterize surfaces to do some similar stuff. So just like with the parametric curves, we had one parameter there, but now we're going to have two parameters instead of one. And so, when we do parametric surfaces, we basically get stuff hopefully I have enough space here. So we typically use u and v. So x of u and v, and then we'd have y of u and v, and then z of u and v. And so it's basically u and v are down here in the plane, right? There's some point in xy space or uv space, right? And then at any given uv, you are plotting a vector, and the vectors, the tip of the vector ends on the surface. And so if you can just kind of keep doing that over and over and over again, right, infinitely many times, you basically get a combination of all these different points, and all those different points build up the surface, and that's how you do it. So it's the same way that you do parametric curves. You can just kind of keep taking that idea up a dimension and do parametric surfaces. So fairly straightforward stuff. I think once you've seen parametric curves, this stuff that I'll talk about today is going to make a lot of sense. So just to start off kind of simple here, say we have we want to find the parametric representation of a sphere. So for this, what I would do is I would utilize what we know about spherical coordinates, right? So we have spherical coordinates is just x equals rho sine phi, right, cos theta. Y is rho sine phi sine theta, and z is rho cos phi. And so so rho is like our radius, basically, of the sphere, right? So if we have radius A, we could just take my spherical coordinates, right? And literally just change rho to... So what we could do here is, if we want to turn this into a parametric surface, basically just take what we know from spherical coordinates and change out the rho to just be the radius of the sphere, which is A, right? So this one would just simply kind of look like this vector. We'd have like A sine phi cos theta, then we'd have A sine phi sine theta, and A cos phi. So it doesn't always have to be that like the u and the v that I had, in this previous slide are what we use. We just typically use u and v kind of as like dummy variables to talk about how there's two parameters to a surface like this. But my two parameters might make more sense to be used as like angles for something like a sphere, because you want to talk about the rotational like polar angle and then the angle that comes down from z, the phi one, right? So this is kind of how I sort of think of a sphere given parametric surface. So another common thing that we do when it comes to parameterizing surfaces is if the surface is like an elliptic paraboloid, or just something that basically the z is in terms of just x and y, what we basically can do is we can just be like, okay, we're going to let x equals x, y equal y, and then z equal x squared plus 2y squared. So that does parameterize it just fine. So, we literally would just kind of write xy, x squared plus 2y squared. And so anytime basically the function is just a function of x and y or something, you can just make this the f of xy, and then you can just pop that in here and just make this x and this y. If you want to use Math 3D, so this is just again here Math 3D, you can't really use x and y though. Its default is u and v. So of course you could just be, if you wanted to get this thing, you go to the parametric surface and then you just do uv and then u squared plus 2v squared, right? And that would do it. So this is a very common trick that we do for parameterizing things that are just like functions of x and y. And also you could do this, right, if it was like a function of y and z, you can let like x equal y, the function of y z, and then let y be y and z be z. So anytime you get something where like one variable is in terms of the other two, this is kind of the trick for parameterizing. Another one that we see a lot of times is surfaces of revolution. And so there's kind of a common trick with these ones too. So say I want to find parametric equations for the surface generated by rotating y equals sine of x around the x-axis. So the way you kind of think about this is I think about it like a circle around the x-axis, right? And from that perspective, the y-axis is sort of like what we normally think of, like if we look straight on, the y-axis kind of acts as an x-axis, right? And the z-axis acts as sort of a y, right? So the z is the vertical and the y is the horizontal. And so the trick is to kind of think in polar, basically. I'm just going to kind of put it in quotes. Basically, we're used to x equals r cos theta and y equals r sine theta. But more importantly, the x is the horizontal. The cosine is associated with the horizontal, and the sine is associated with the vertical. So what we can do is we basically, if we wanted to rotate around the x-axis, we can just let x equals x, okay? And if we wanted to rotate around y, we could do y equals y. And then the function is like the f of x is basically what will be my radius, right? And so just like in this picture, it's saying, like f of x, like whatever thing I have out here that f of x will be the thing that I'm rotating around, right? And so I can let my r be like f of x. So I can let y, which really acts as a horizontal distance in this perspective, y acts as f of x cos x, and then z can act as f of x sine x, so or sine theta. So the z is just based on the triangle, right? It's going to be the f of x is my like radius, and then you just do sine, right? Z equals you just do sine of theta is z over f of x, and so you just solve for z, right? And so if you wanted to do that's like for any arbitrary surface that you get by rotating around the x-axis. So if I wanted to do this function rotated around, then all I would basically do is I just replace my f of x with sine of x. So I have x for x because I'm rotating around the x-axis, sine of x, and then cos, and then sine of x again, and then sine theta. And so these two parts right here is what helps give me the rotation around the axis, right? And then the function just gets popped in there, and then you just keep this the same if that's what you want to rotate around. And so I did the thing where I just made x basically u, and theta is v here. And if I let x run from negative 2 pi to 6 pi, and v run from 0 to 2 pi, so that's my angle, v is the angle, then you get this kind of weird, sine of x rotation thing, right? And so, you can do that for any axis too. You just change whichever one is fixed, right? So if you wanted to do it for a rotation around the y-axis, you would just make like y equals y, and then adjust it from there. And if you were doing it around the y-axis, then x is like the horizontal and z is like the vertical. Okay, so you would need to have like x is the cos one and z is the sine one. But yeah, that's like a very common trick for some surfaces that you can just get by rotation. The next thing I want to talk about is kind of going back to some stuff that we did before. So I'm going to do a quick little review of surface area for these surfaces, and I'm going to show you kind of a nice connection to some stuff we've done before, now that we've seen a little bit about parameterizing surfaces. So I'm not going to go through all this in detail because I have another video on it. If you go back to like the 15.5 video, you can see all this there. But we talked about how if we want to do surface area of something, we can use like an approximation of a tangent plane. That's what this T is, capital T. And if you made these rectangles increasingly more common, like you made more of them, you let M and N, which is like the partitioning of the different directions here, if you let those go to infinity, so you have like super small rectangles or squares down here, then that would, if you zoom in and zoom in and zoom in and you just have like a super small little square, then that super small square will actually approximate the surface really well, and then you just add up all those different, the area of those rectangles, right? And as you add them all up, and they were super small, then you would basically be adding up the true like surface area, right? So we talked about that idea there, and then we talked about, well, how do we even get this area approximation of these like tangent planes? And that was like a chapter 12 thing. The area of the magnitude of A cross B is the area of the parallelogram that's formed by them. So like A being this thing and B being that thing. And so then that kind of became our go-to. We were like, okay, well, how are we going to get A and B? And we talked about that here where we kind of talked about what was changing in the different directions, right? So like there's like kind of these two different parts to like there's like the y and the z kind of directional parts, and so that we built up what a and b are, and then we did the actual magnitude of that cross product, and we arrived at this formula. Okay, and then we just did a problem down here where we could get the actual surface area. So with parameterized surfaces, a lot of this is honestly just super easy because we have like a better language to describe how to do this. So if you have like some R of UV parameterized surface, right, then the surface area of that thing is truly just the double integral of this is the magnitude of the cross product. So the book uses the single bar. I like the double bar. But it's just the magnitude of the cross product of R with respect to U and R with respect crossed with R with respect to V. So, you just take every R of U is just everything in here with respect to U, Y with U, Z with U, and then X with V, Y with V, Z with V. So if we wanted to do the surface area of a sphere of radius A, which we should hopefully know the answer to, we would just start with our parametric surface equation, which is this, right? And then we would just do the, we have to have R with respect to phi, and then R with respect to theta. So R with respect to phi would equal that thing. And then we need R with respect to theta, which would equal that guy. And then now we have this really just nice, straightforward way right here to find surface area. If we have those two vectors, we can just cross them and take the magnitude and of that cross product, and then just do the double integral of that, and it will truly just give us the surface area. So I'm going to start by doing the magnitude of the cross product. So we're going to start off and just do R of phi crossed with R of theta. So we get that if you just do out the cross product. And then we need to do the magnitude of it, right? And this is actually where some stuff's going to start to simplify really nicely. So, we'll need to take the square root of this whole thing, but we're going to have a to the fourth sine to the fourth phi cosine squared theta plus a to the fourth sine to the fourth phi sine squared theta plus a to the fourth sine squared phi cos squared phi. And then we have a square root of all that. And if you look inside here, so you can take out a to the fourth sine to the fourth phi, right? And then you would have a sine squared plus a cosine squared. So then that would basically go away, right? And then, so then you would have, I guess we'll just write it out here. So then you have a to the fourth sine to the fourth phi plus a to the fourth sine squared phi cos squared phi. And so now you want to take out a to the fourth sine squared phi, and then you would have sine squared phi plus cosine squared phi. And now everything's going to be really nice because, again, you get, in here a 1, right? And then you'll have just a squared, and then the square root of sine squared is like a sine phi there. And so that is my magnitude of the cross product, right? And so all you got to do is, which maybe this doesn't feel like a super short thing, but now we basically, to do the surface area of this thing, we can just go from 0 to pi in phi, and then 0 to 2 pi in theta. And we're going to do the double integral of a squared sine phi. And if you do this out, it truly will equal what you would hope it would equal. So basically, it's one of those where you could pull out the a squared, right? We don't need that. Then it's one of those where they're like separable. It's like a separable a double integral. So there's no theta that's kind of in there. So we could really just do a multiply by 2 pi for the theta integral. And so then we just have the integral from 0 to pi of sine phi, d phi. And so from that, you would get you get 2 out of this part right here if you do that integral out. And so then we get a squared times 2 pi times 2, which is, of course, 4. We'll just do pi a squared. And that is what the surface area of a sphere is, right? And so it might look like a lot of work, but honestly, if you can get parametric equations, it's a fairly straightforward way to get surface area. And there's so many things in applied math and science where you would basically need the parametric equations. And so you're already working with them, and it's just a nice way that we can see this computation just done a lot more straightforwardly than before. And I wanted to make a connection here just at the end to what we saw with our surface area formula before. So this is kind of what you're probably more used to. And we talked about this, and we talked about, back here, talking about how to get to that. And you can still use this, but it actually can relate to what we're doing right now as well. So if you have a function that is one of these z equals f of xy functions, then the r with respect to x would just be 1, right? Nothing for the y, and then f with respect to x, right? And whoops, let's do this. And then r with respect to y is nothing here, 1 here, and then f with respect to y. So if you do r with respect to x crossed with r with respect to y, you get, I hat, j hat, k hat, then you get 1, 0, f with respect to x, 0, 1, f with respect to y. And if you compute this cross product out, you get minus f with respect to x, minus f with respect to y, and 1, right? And so you're probably seeing where this is going. So then if you just do the double integral of the magnitude of this cross product, right, it would be the square root of f with respect to x squared, the negative is going to disappear, and then f with respect to y squared, and then 1. dA, whatever the a is. So that is actually just a nice way to see what we just did and how it connects to what we kind of built up before. So this was sort of just a consequence of this special parameterization for a surface. So anytime you have one of these, you can still just use this if you want, but you could also still do the cross product magnitude of the cross product thing. So so this is a handy kind of formula to know for surface area of parametric surfaces.